Okay, it's time. So let's start the session of the learning and training sports and movement. I'm the session chair of this session, Katsutoshi Masai from Kyushu University. The first presentation is about teaching dance with mixed reality mirrors. The presenter is Stephan. Let's get started.
Okay. Well, thank you very much for the introduction. I hope you can all hear me clearly. First of all, I will have to apologize that I'm giving this presentation because the person who should really give this presentation is Anna Treffer. She was a postgraduate student in our lab in the HIT lab New Zealand. And yeah, unfortunately, we couldn't, and she couldn't arrange travel to come here. So you need to deal with me. Adrian couldn't come as well. So here I am. Yes, so teaching dance with mixed reality mirrors. To immediately jump into why we did it, we really wanted to answer this research question. So we wanted to know whether a virtual instructor combined with visual feedback can support dance learning using a mixed reality mirror. Why did we ask this question? Well, several reasons, several design decisions that we have taken here. First of all, utilizing a mixed reality mirror. I will explain in a minute what it is, but just imagine it as a smart mirror for now. The idea is if you go in a dance studio and learn a dance, you also stand in front of a mirror. So students who learn dancing are actually quite familiar with a mirror. It's very typically how they normally train. It doesn't hinder the movements as compared, for example, using a head-mounted display. Also, with a head-mounted display, you would have the issue that you probably would have to display something on the body of the person who wants to support dance. Okay, I hope nobody is going to fall asleep now. But obviously, the slides are way better in this way. Yes, and normally you also have an instructor in a dance studio who tells you how to improve your dance, what is the next step, how you need to change your body posture and your movements. This instructor in a dance studio, okay, good morning, might actually also mimic the dance movements so that you can copy what you need to do in the dance. Yes, so we tried now to bring this all together using mixed reality technology in a mirror in which a dancer would see him or herself in addition to a virtual instructor, in addition to feedback on how to move into the correct position. So from a hardware and software perspective, we used a laser projector mounted on the ceiling that created a really large mirror in front of the dancer, the user that is depicted here. We used a white backdrop to have a really clear contrast for all the dancers coming in so that we can actually clearly see the posture and give feedback. And we used an Azure Connect to track the motion of the persons. How did we go about the design? And especially in this case, about the design of the visual feedback modes. We did a literature review and looked into how visual feedback was given so far when training, let's say, physical motions. Based on that, we created initial first visual feedback modes, but then we interviewed 3 experts, meaning like professional dance instructors, and in order to get their feedback on how they would actually like to see visual feedback provided to dance students. Based on these interviews and based on the literature review, we in the end had about 23 different visual feedback modes, which we put into an online survey where we asked people to vote on the ones that they preferred the most. Of the 23, 10 were overlaying the avatar over the dancer, and about, okay, something is happening behind me, in case you hear some plastic noise, it's not me. And 13 were putting the avatar next to the dancer and also the virtual feedback next to the dancer. Of these 23, in the end, 3 made it. All 3 visual feedback modes that we then had in the end actually overlaid the avatar over the dancer and provided feedback on how to correct the position. So what you can see here is basically the first feedback mode is spheres that just shows, let's say, spheres around the joints of your body. And like with all feedback modes, the color basically indicates how far you deviate from the correct position. And we used when it was fully green, you were or the joint was in the correct position, and when it was fully red, yes, the joint was more than 30 centimeters off the correct position. Orange was in between, about 15 centimeters off the correct position. So the spheres move basically with your body and indicate how far you deviate from the virtual instructor. The rubber bands are connected to your body, but are also connected to the body of the virtual avatar or virtual instructor, basically give you some directional guidance on where and in which direction you need to move that joint. And the arrows, again, were connected to your body, but the arrows, or the arrowhead basically indicated in which direction you need to move this joint. To visualize this, that's slow motion. Well, in fact, that's the training mode that we used during the experiments, so that people using and trying to learn a certain dance move could basically move slowly into the position. So you can see here how the virtual instructor shows the move and how the dance student, in fact, that's actually Anna, who worked on that, moved into position. And she could have done better because she really knew the dance moves. I was the odd one in the bunch. It took me a long time to learn it. This is how the rubber bands visual feedback mode looked like. And again, you can see how it actually works. And for the arrows, that's the third mode. Okay, so this was on the design of the feedback modes. In order to run an experiment, we aimed at an within-subject design, and we had 3 feedback modes. We designed, or Anna designed, 3 different dance routines. They were all inspired by beginner hip-hop and contemporary tutorials that she found on YouTube, on contemporary dance movies. They were designed to be of approximately equal difficulty. They had 12, well, this one is dance number 1 that has 13 poses, the other dances had 12 poses, but this one also had a neutral position where you actually didn't have to do much, so we consider that quite similar. Within the dances, or between the dances, there was enough variation in between the poses so that we could avoid learning effects. So if you could do one dance, that didn't mean you could do the other, believe me. And the routines were initially motion captured using an OptiTrack motion capture system to animate the instructor avatar in Unity. And that's one demo of a dance. Some people asked me whether we could dance in this session. I said, like, well, I have the instruction video here. If anyone wants to volunteer, I'm not doing that. You can come up and face the screen. No, that's all right. But if you want to, we can do that afterwards when nobody's watching. Yes, so that was the first dance. The system in general worked like this. The instructor avatar shows up and animates the next pose that you as a dance student had to move in that sequence. The user or student needs to move to match the avatar following the visual feedback mode, and the avatar stops moving or waits in that pose until the pose is matched. Always, because we really had people that struggled finding the correct pose, the user or the student could ask to manually override to move to the next pose, but that was then counted as a pose, or we counted the error still. So, but we later on in the experiment also counted the amount of manual overrides that we had to do. So as I said, it was a within subject study. The order of modes and mapping of modes was randomized per dance. We get a full speed demonstration initially, then we had 3 practice rounds in slow motion, and then we did 1 performance dance at full speed without the feedback. Overall, in the end, we had about 40 participants, 19 female, 19 male, and the experience with regard to dancing was quite mixed. Measures that we used, we did some performance evaluation, and that was mainly about the overall pose errors, the time the avatar stopped and waited until somebody moved in the correct pose, and the amount of manual overrides. We used the attractive questionnaire to look into appeal and usability, and we did some subjective preference and experience ranking of the feedback modes after the experiment by, asking the participants to rank them, and did a post-experiment interview. Based on the expert interviews and the online feedback, we had two hypotheses. One that's based on the experts. The experts really thought that spheres and rubber bands was the preference of the experts, and users preferred arrows over rubber bands over spheres. That was what was in hypothesis 2. So this is how we went into the experiment. What we in the end learned within the performance evaluation, there was no significant difference, though overall the values favored spheres over rubber bands over arrows. The same with the time the avatar stopped, so the time was stopped, or the avatar was more waiting for the user to follow up in the spheres mode, then in the rubber bands mode, and then in the arrows mode. And we also had the most manual overrides in the spheres mode, and then the rubber bands, and then the arrows. So overall, let's say, even if not significant, the arrows mode was working better. In the attractive questionnaire, we basically learned that there's a significant difference between arrows and rubber bands, and arrows and spheres, but not between spheres and rubber bands. So again, arrows seem to be the preferred option here. Also in the feedback rankings that we had in the end, users preferred and ranked rubber bands, no, arrows, no. This is the interesting one. Oh, that's my mistake. Let me see. Yes, there's an error on that slide because in fact, oh no, sorry. In the feedback rankings, the users preferred the spheres over the rubber bands and over the arrows, yes. And that's just opposite to the performance evaluation. So because I'm probably running out of time, so on the feedback, spheres was preferred because users thought they are simple and clear, non-intrusive. The rubber bands said, like, well, it's good that they chose the distance from the user joints to the target position, but we got quite some feedback that it was difficult to estimate depth in the movements. And arrows were kind of considered as most confusing, though it showed a clear direction. So basically the arrows attached to your body with the arrowheads were considered as too intrusive and too difficult to follow and too overwhelming. Still though, yes, it helped users to clearly, at least not significantly, but to perform the dances with less errors. Okay, let me skip this one. So surprisingly, we learned that despite our hypotheses based on the expert interviews and the online evaluation and questionnaire that we had in the beginning, that the arrows yielded the best performance. So our first hypothesis was rejected. That was based on the expert interviews. The spheres yielded the worst performance, but were ranked the best. So also our second hypothesis was rejected, which is in general not too bad because we still learned that the feedback mode with the arrows led to the lowest error rates. What we need to do in future, though, is to really think how we can address the participants' feedback to make the arrow mode as redesign it in a way so that it is not overwhelming and still guiding. Other things that we really would like to look into is we had a few participants like singing along when they did the dances, so they actually asked whether they could have music with the dances because it would help them to memorize the moves. And future work will definitely also look into the fact to get into the right depth position. So whenever you stand in the dance position and have to move your arm back or your hand back, that's quite difficult to see in the mirror and to gorgeous. So we have a few ideas about that. And yes, future will tell. Thank you very much for your attention.
Thank you for the presentation. Any question from the audience?
Hi, thanks for the presentation. Very interesting research. Just a short question. Do you have a feeling how these techniques could be adapted for dance scenarios with multiple people? And I mean, not only in a sense that they are doing a choreography being apart from each other, but actually a bit more closely dancing? Or could you foresee maybe some problems there?
Well, I think most of the people in the room will probably have used the Kinect, so I don't see how that can be done with the Kinect, because the Kinect gets confused if there's just a second person somewhere close to it. So you would have to look for some motion tracking system that allows to track joint positions of multiple users. We happen to have a quite large OptiTrack installation, so we could make that happen. Yes, but then you would run to the, yeah, well, yes, with a mixed reality mirror, you could still work with it. Though I think with dance with several people, you probably will not stand still. So the moment you start moving, you get even more depth perception issues. So what we do at the moment is to look into alternative displays like dome displays, cave displays, so that you can get more feedback even when you turn around. Yeah.
Thank you. One quick question from...
Thank you. Thanks for the talk. Slightly beyond the scope of your study, but did you notice an impact on the Kinect latency on the feedback? Because it does have a pretty much latency, although it's the same in all conditions. It should be the same.
And that's mainly because the feedback was only provided during the training routine when the avatar was really moving slow. So when you had to perform the dance, actually when you had to show whether you have learned the dance in the 4th round, so I skipped about that a bit quickly. So you first saw the dance, then you could practice it 3 times with feedback, and then you had to perform the dance without any kind of feedback to see whether you could memorize it and really could learn the dance. So because, yeah, the training part was slow, we didn't notice anything. Yeah.
Thank you.
One quick question. Okay.
Okay. Seriously. Okay. Thank you.
Thanks. Very interesting work. We did something similar about fitness training a while back, and you say you haven't really thought about the 3rd dimension, the depth, yet. Do you think mirroring will work well? Because it seemed to us, so now we are confronted, and if I use my right hand, you would use the left hand.
Yep.
But if I go like this, eventually there is this break, and all of a sudden this will be my right hand corresponding to your right hand. So have you any ideas when to switch maybe from mirroring to something else, or how to go about that?
Yes, we have thought about it, and I'm happy to say that Anna stayed behind in the lab, is doing her PhD with me. So, and we exactly will look into how to solve that. So we're currently setting up ideas. And as I said, at the moment we look mainly into alternative display forms. So that doesn't solve the left and right thing, but it solves the issue that the moment you turn around and you don't see the mirror anymore, we could actually move the avatar with you in the dome display, and you would still get continuous feedback. It's great, but it's just an idea. We have no idea how and if that works, so hopefully we'll be back, tell you more about this. Yeah.
Okay, thank you for the presentation. So the next one is from the online, and the title is The Pin Between Walls, Training Table Tennis Novice Players in Real Environment for Virtual Reality Competitions. From the Kissinger.
Hi everyone, my name is Kissinger Sunday, and I'm a third-year PhD candidate at the Faculty of Computer Science at Dalhousie University. On behalf of my collaborators, Yiwei, Junwei, Neyedli, Wehbe, Ufuk, and Mayra, I'll be presenting our work titled Thinking Between Worlds, Training Table Tennis Novice Players in Real Environments for Virtual Reality Competitions. Now, VR is becoming a mainstream technology as modern virtual reality head-mounted displays offers a realistic experience in terms of graphics and tracking, and they are accessible to the general public. For example, the Meta VR head-mounted display has sold over 20 million devices, and one of the reasons driving this is the allure of gaming, including exa games such as Beat Saber, Mini Golf VR, and the VR table tennis. We focus on VR table tennis in this work because it's one of the most popular sports in VR. For example, the 11 table tennis has a substantial user community of over 298,000 players. And in VR table tennis, 2 or 4 players use a paddle to volley a ball across a table with the aim of sending the ball across to the opponent's side so that the opponent fails to return it successfully. While previous works have focused on training players in virtual reality environments for real life tasks, to the best of my knowledge, this is the first study to investigate training real-life players for VR competitions, simply because real life offers opportunities for players to effectively train and engage, addressing scenarios of diminished realism and limited access to perceptual affordances, such as depth perception, weightlessness of the ball, haptic feedback issues, and a host of other issues. Moreover, a survey of table tennis players shows that these players prefer training in real life for VR competitions. In fact, some of these players talked about hiring real life coaches to help them train for VR games, because according to them, it helps them in basic task improvements such as forehand skills, spinning effects, their body conditioning and positioning as well. Based on this, in this work, we hired a real-life coach to train participants in real life for VR competitions to address 2 research questions. The first research question is, what are the skills that can be trained in real life and transferred to VR environments? And also, what are the technological challenges players encounter in VR? To address this, we hired 12 participants to train them in real life. And these participants needed to have never played VR table tennis before and played real life table tennis less than once a month, and also passed a skill test. We administered a skill test to ensure that these participants were truly novices. For the pre-training stage, we assessed participants' baseline skills in VR. And after this stage was completed, we hired an expert coach to train participants for 5 consecutive days in real life. We divided the players into 4 groups of 3 to ensure that the room could accommodate these players. And after the training was completed, we assessed their skills in the post-training session in VR. And after this post-training session was completed, we administered some survey instruments to gain understanding about their level of immersion, physical activity, enjoyment, and also simulation sickness. During the training stages, we trained them on different skills, including short serve, forehand, spinning, footwork, and for the final day, they engaged in matches. We assessed them on various skills, on how they were able to effectively use these skills, and we awarded scores up to a game of 11 following the international table tennis rubric system. We actually have interesting results in this study. For the first research question, we discovered that all the 16 skill scores improved significantly. And for that test, using the Benjamin Hodgberg procedure shows that these results were truly significant. For the survey instruments we administered to the participants, we discovered that they were positively rated. However, for the simulation sickness, we found out that the participants experienced very low simulation sickness in VR. For the qualitative results, we discovered that participants complained about graphic glitches. Others talked about haptic feedback, ball control, and also depth perception were issues that the participants mentioned. But the limitations in playing table tennis in real life, the participant talked about difficulty finding opponents in real life, space constraints, picking up balls, also adjusting the table heights. With a perception of skill transfer to VR, we talked about basic skills transfer, including consistency, and one of the participants talked about spinning difficult in VR. In this study, we conducted a pre and post experimental design to ascertain what are the skills that could actually be trained in real life and transferred to VR environments, and what are the technological issues participants encounter in VR. We discovered that these participants improved in all skills, and also we identified various technological limitations that hampered their experience in VR. Based on this, we offered some design recommendations to help both software developers and table tennis players as well. For the first recommendation, we suggest integrating real-life training as supplementary to VR training. Participants improved in all skills after training in real life, and these participants were able to navigate their environment in the VR session. So I believe that if real-life training could be incorporated as part of their training regimens for them to understand how this thing works in real life before starting their play in VR, it will be a long way in enhancing their performance. We also suggest developers to focus on user-centered design. In our study, we recruited only novice players to get their feedback. We believe getting feedback from professional players will improve overall user design that actually meets users' need. We also recommend following training protocols produced in real life to improve VR training applications. And we actually recommend developers to integrate our protocol when designing training applications for players, which we believe that it will help them in improving their performance, as our protocol really improved players' performance overall. We also recommend developers to optimize game physics with concentration on the ball. Based on our qualitative results, we recommend developers to focus on two aspects. The first one is the ball dynamics and collision boxes. And the second aspect is the spinning effects, so that it will closely mimic that of real life. We also recommend developers to mitigate VR limitations for playability and accessibility. Players were able to pass through the ball to return a short serve in our study, which actually violates the rules of table tennis play. Hence, we recommend developers to consider mitigating haptic feedback issues so that it will enhance overall user performance. Finally, we recommend developers to incorporate visual coach and training protocol for VR training applications in real time. Our coach was able to provide various forms of feedback, including visual, verbal, and kinesthetic feedback to players, which helps them in their performance. We believe that if this can be replicated in VR environments, it will go a long way in helping players improve. Our contributions in this work includes the quantification of 16 essential skills for VR table tennis players, and also we adapted a real-life training protocol that has established efficacy, and we validated it with 12 users. We also identified technological issues that our players complain about in VR. And finally, we provided design recommendations which will help both players and VR training application developers. Our results can also be extended to other domains that require fast hand-eye coordination, like drones. They can be able to understand the speed sensation in real life for them to be able to use VR to pilot these drones. Thank you so much for listening, and please do not forget to reach out to me via my LinkedIn or email if you have any questions or for further collaborations. Thank you so much.
Thank you. We have time for 2 questions. Any question from the audience? Oh, can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah, yeah, great. So what kind of required skills are different between the VR system and AR live system?
Please, can you repeat the question?
So what are the differences between what are the different the skills that's required for the real life training and virtual reality training? Is there a similar skill or a different skill for doing
For
the
VR and real life, actually, it's basically the same skill,
or
both for real life and for VR. They are because we will try to make VR as similar to real life as possible because we have various competitions that are actually going on now in VR table tennis. So the same role in real life is also applicable to VR environment. So basically, it's the same skill that we actually investigated.
okay. Any question? Okay, thank you for the presentation.
All right, thank you so much for having me.
So the next talk is enhancing eye-hand coordination in volleyball players, a comparative analysis of VR, AR, and 2D display technologies and task instructions. The presenter is the Nour. Yeah, okay. When it's ready, go ahead.
So, hello everyone. Thank you for coming to this session. So, I am Nour Hatira, a master's student in Kadir Has University, Istanbul, Turkey, and I came here to present our research findings about an eye-hand coordination training system for volleyball players. So, first we start to talk about the use of VR and AR technologies in sports training. VR and AR are transforming the way athletes train by allowing for controlled, repeatable, and customized training sessions. So each one of these technologies has its own advantages. So as you can see here, VR immerses athletes in a fully virtual environment, which is more suitable for home-based training. On the other hand, AR trains in natural surroundings with overlaying some digital content, which is for more effective training. So apart from providing a unique experience for the athlete, it also offers some advantages for the coaches. It can help coaches with performance assessment as they can monitor the progress from distance. Also, they can opt for a data-driven performance tracking by collecting some detailed data for some specific movement and then tailor the missions accordingly. Let's focus on one specific task which is important for athletes. So traditionally, the eye-hand coordination task is done through locating and reaching to targets. So nowadays it is done through some similar devices where the athlete have to locate the light and touch it before it disappears. So studies have shown that repetitive practice on such devices enhances the eye-hand coordination and the motor performance. So previously, many studies were conducted aiming to build an effective eye-hand coordination training system. As we can see here, some of our previous studies made it in 2D screen, VR, and AR. So our aim now is to bridge some gaps identified earlier in our previous studies, and then to try this setup with the sports population. So to do this, we have some research questions regarding which display technology is more suitable to train volleyball players, and if the task instructions would affect the performance of the player, and would the effective throughput be an effective performance assessment for the eye-hand coordination training system. So to achieve our objectives, we built an eye-hand coordination training system on Unity, which features a 5x6 button grid. We did the same design over 3 display technologies, which are VR, AR, and 2D touchscreen. In each display, the user plays 3 rounds. In each round, there is a different target size. And for each target size, there are 3 possible target distances. So the user plays have to touch 20 targets for each target distance, which means 60 targets per round and 180 targets per display technology. So the game principle is simple. A yellow button will pop up and you have to touch it. If you touch it in a correct way, it will become green. If you touch it in a wrong way, it will become red. So here is briefly the game. Yeah. Okay, so we did some minor adjustments for the VR and the AR headsets. For example, we added the white cursor for the on the index finger for the VR avatar, and we added a skeleton on top of the hand to allow for smooth interaction on the AR headset. And then there is a blue cursor on the index finger on the AR headset. We also have noticed that there might be some visual distraction because of the background on AR. So for our user study, we asked the users to face an empty wall. So our user study incorporated 16 professional volleyball players. They played the same game over 3 display technologies, and they played 3 rounds in each display technologies. All of them were counterbalanced among participants. So our user study spanned 8 training days. And the participants were asked to fill out 2 questionnaires, one on the pre-training and one in the post-training regarding their preferences. We divided our participants into 4 task instruction groups. The first group was instructed to select the targets as fast as possible. The next group was instructed to minimize the number of errors. Then the group after it, they were instructed to select the target at their midpoint. And the last group, they were given no instructions. We evaluated our findings by 5 evaluation metrics. The first one is the duration time, which is basically the reaction time. The second evaluation metric is the error rate. The next evaluation metric is the precision, which is basically the consistency in choosing the same point in the target. And then accuracy, which is the consistency in choosing the center of the target, which is the midpoint of the target. And then the last evaluation metric is throughput. So what is throughput? Yeah. So throughput is a measure that is based on Fitts law, so which is briefly the ratio of the effective index of difficulty over the movement time. So here we are using the throughput as a brief performance assessment to get an overall idea about if the participant performance is improving or it's not improving. So we started our analysis by observing the data for the pre- and post-training days. So for both time and error rate, so we found out that all participants group statistically improved in the post-training compared to the pre-training. In terms of precision and accuracy, all groups except the speed focus group significantly improved in the post-training compared to the pre-training. And finally, in terms of throughput, we found out that all participants group improved in the post-training compared to the pre-training. Now, to get a better understanding about our findings, we plotted the longitudinal training data, and then we had a look at our data. We found that some significant differences, so we went further for post-hoc analysis. So in terms of time, the way participants selected the target differed significantly among the display technologies. We found out that participants selected were the fastest using VR head-mounted device, and they were the slowest using the AR. And for the error rate, they made the fewest errors in the 2D display, and there was no significant difference between the AR and VR headsets. In terms of precision and accuracy, both participants selected the targets with statistical differences in the 3 display technologies. So they were more accurate and more precise in the 2D display, and they showed the least accuracy and precision in the VR headset. In terms of throughput, participants made the highest performance using the 2D display, and then they showed the lowest performance using the AR headset. Now, when comparing the results of the task instruction groups, we found out that in terms of time, the speed focus group was the fastest, and then the accuracy focus group was the slowest. In terms of the error rate, we found out that the accuracy and error focus group showed the fewest errors, and the highest errors were with the speed focus group. So in terms of precision and accuracy, all participants groups showed different performance, where the highest precision and accuracy performance was with the accuracy focus group, and where the lowest performance was with the speed focus group. And finally, in terms of throughput, we found out that speed focus group showed the highest overall performance, and the accuracy focus group showed the lowest performance. So, as we have mentioned earlier, we asked the participants to select a questionnaire regarding their preferences. We found out that most participants selected, when asked about their best environment, most participants selected VR and AR headset over the 2D display, which is an important note for us since our quantitative results showed the inverse. When asked about the worst environment, some participants did not prefer the AR because of some technical issues, mainly related to the reflection of the light. And some participants selected the 2D display. They said that it limits their movement. So now, putting everything together and addressing our research questions. So in terms of subjective feedback, participants preferred VR and AR, but not the 2D display. And in terms of quantitative results, we found out that the 2D display led to better motor performance than VR and AR. So in here, we think that if our subjective feedback found out that the VR and AR are better than the 2D display, we think that we can push further for more extended training days, and we might find some better results with the headsets more than the 2D display. Addressing our second research question, so our results emphasize the significant impact of varied task instruction on professional volleyball players. For instance, accuracy-focused participants helps them increase not only their accuracy but also their precision in selecting the targets. Error focus group or accuracy focus groups training, they helps them to make fewer errors at the end of the trainings, and the speed focus group helps them increase their speed. So finally, addressing our last research question, would the throughput be an effective measure for our eye-hand coordination training system? So our findings revealed an overall increase in participants' throughput across all the training days. We also found out that if they performed good in that day, their throughput increased. In case they have a drop in their performance, the throughput decreased. So we believe that throughput can be an effective measure for the eye-hand coordination training system. Thank you so much for listening.
Now let's move on to the Q&A session. Any question? Okay.
Thank you very much for this presentation. It might be an obvious question, but how far do you think that the hardware actually impacted your results? So if you would have faster hand tracking and more accurate hand tracking,
Yeah, sure.
Have you thought about that using a different system?
Actually, in our lab, we have MetaQuest 2 and we have HoloLens 2. And so mainly they didn't prefer the AR headset because of some reflection of the light, some issues related to these technical issues. And yeah, no, we didn't try with different headsets, but with the subjective comments, we still got that people enjoyed more using the headset than the 2D display. Yeah, thank you.
Thank you. Any question from the audience? Okay.
Hello, thank you for the presentation.
Thank you.
I think the training that you have performed can be beneficial for sports players of different types.
Yeah, sure.
Is there any reason why you specifically chose volleyball?
So thank you for the question. Actually, in our university, we do have a professional volleyball team and rowing team. So we went with the volleyball team. Then we suggested that we will generalize our findings for this post training. Then in the reviewing stage, we got that comment of that if we did the training with volleyball player, we might not know the findings for other sports. So that's why we made it so specific for volleyball players. Thank you.
Thank you. There's one quick question time. Anyone? Okay, thank you very much.
Thank you so much.
So the final presentation is inter-brain synchrony in remote AR education. Can warming up activities positively impact educational quality? The presentation is from Jaehwan. Okay.
My name is Jaehwan from Hanyang University, South Korea. I collaborate with Myeongul Jung and Kangwoo Kenny Kim for this work, and I am going to talk about this. The paper title is Interbrain Synchrony in Remote AR Education. Can warming up activities positively impact education quality? First, I will tell you the summary of this study. This study investigates the effect of prior physical synchrony in the remote AR education. So like this figure, we found that prior physical synchrony positively affect on brain synchrony and students' learning outcome. Next, I will tell you about background and motivation of this study. AR technology in education. As you know, AR has large potential in education field. It can visualize abstract concepts to gain knowledge easier and provide virtual avatars, allow students to attend lecture remotely with a sense of being present in the classroom. So, previous AR study focused on visualization of contents and avatar appearance. For example, they visualized organic compounds which are to observe in real life and investigated the appearance of avatar to which type of avatars positively influence the remote interaction experience. Those of study have contributed to improve remote education quality. However, the quality also can be different depending on avatar's behavior. So why avatar's behavior is important? Because people feel the communication is going well through the other person's responses. One of good example is interpersonal synchrony. It refers to the phenomenon that people coordinate their nonverbal behavior during interaction. People can feel interaction is going well through physical synchrony, such as mimicking gesture. Furthermore, this experience can lead to brain synchrony. Therefore, interpersonal synchrony is one of the most important factors in the interaction. So there are several studies investigate interpersonal synchrony during interaction. They found that interpersonal synchrony induced in remote environment such as video chat and mixed reality. However, previous studies have not investigated interpersonal synchrony during remote AR education, even though face-to-face research have considered this issue as a major concern. In the face-to-face studies, they show that physical synchrony positively impacts on learning outcome, brain synchrony, and social closeness. So in this study, we also investigate the effect of prior physical synchrony on learning outcome, brain synchrony, and social closeness in the remote AR education. We recruit 43 participants in this study and use Unity Engine for software and use Anil Glass, Galaxy smartphone, and FNURS Lite for hardware. There are 3 phases in this experiment: a moving phase, running phase, and testing phase. And there are 2 conditions in the moving phase: physical synchrony condition and asynchronous conditions. In the moving phase, we conducted finger tricking tasks for inducing synchronous and asynchronous experience. They move 1/8 of circle per upbeat sound. For example, this is a teacher hand, and this is a student hand. In the synchrony condition, they move finger with same direction and BPM, like this. In the asynchronous condition, they move finger with different direction and BPM. If students BPM faster double times than teacher, they move like this. so they can experience synchrony and asynchronous interaction in the movie phase. In the learning phase, participants learn 8 English words from teacher. Each word teacher talk pronunciation and meaning of Korean, and the example sentence repeatedly for 40 seconds. And in testing phase, participants fill meaning of words and blanks the example sentence on the test paper. This is the figure which presents the experimental procedure of this study. We use 3 dependent measures in this study. First, learning outcome from word test result. Second, brain synchrony value range from 0 to 1. High value means they are more synchronized. Third, social closeness, we measure it through 3 questionnaires. Let's look at the results. In learning outcome, the results show that the physical synchrony condition is higher than asynchrony condition, which means that physical synchrony activities with the teacher avatar can improve students' learning outcome. In brain synchrony, we contain the restriction because it is a baseline of brain synchrony. The ANOVA analysis show that there is main effect in brain synchrony. The post hoc analysis show that synchrony condition higher than asynchronous condition and rest section. Additionally, we compared brain synchrony in 5 brain regions for finding which brain region caused the results. We found that the FPPFC, which is center of prefrontal cortex, caused the brain synchrony results. We conduct correlation analysis between learning outcome and brain synchrony in FPPFC. The results show that there is significant correlation between learning outcome and FPPFC in the synchrony condition. The results indicate that brain synchrony between teacher and student can be used as an indicator to predict students' learning outcome. Finally, in the social closeness, the results show that all questionnaires are higher in synchrony condition than the asynchronous condition. There are 2 main findings in this study. First, we found that the prior physical synchrony promote learning outcome, brain synchrony, and social closeness in the remote AR education. As I mentioned before, AR has advantage in visualization of contents or avatars. If we combine this advantage and our result, it can be a great synergy in the remote AR education. Second, brain synchrony in FPPFC can predict students' learning outcome. FPPFC is related to integration information in working memory. Working memory refers to a brain system that provides temporary storage and manipulation of information. This ability is very, very important to both teacher and student. For example, teachers should manipulate and convey information about English words to the student effectively, and student should receive the information and manipulate it to remember. We consider this brain system is related to education quality and leads to brain synchrony between teacher and students. In conclusion, we found prior physical synchrony between teacher and student has benefit to induce brain synchrony and improve students' learning outcome. Furthermore, we found brain synchrony can be used as an indicator of education quality. We believe this study will inform future research in the remote AR education. There are some limitations in this study, such as need additional samples and provide more social cues for virtual avatars. Thank you for listening.
Thank you for the talk. Any question from the audience? So I have a question. So do you have any insight about how to design the physical synchrony? Like, is it about the complexity or the time-wise?
this finger test is used in face-to-face study from Nozawa research. There are other studies in such like dancing with teacher before the classroom. Thank you.
Okay, thank you. Any question? So I have one more question. Is it possible to extend to one-to-many situation? Like one teacher and the many students do that
Yes,
together?
one teacher.
Okay.
So, yeah, yes.
Okay, thank you very much. Any question from the audience? Any volunteer? Okay, thank you very much for the talk.
Thank you.
So this is the end of the session. Thanks again for the presenters.